All right, so today we're going to do what's called optimization, and different from yesterday where we were looking for maximums and minimums of surfaces, so infinite surfaces. I fluff the sheet, right, do a freeze frame, I have peaks and valleys on the sheet. I have clear maximum and minimum z-values, and maybe even saddle points, okay? But that's looking at a surface. Now we want situations and saying, you know, what's the most amount of money I can make? What's the least amount of time? You know, things of that nature, optimization. But we're going to do it as it applies to graphs because it's easier at first if I do it from a graphing approach. So what I'm going to do is start with what I do in Calc 1. I'm going to start with a really easy problem in Calc 1 to introduce, okay, how did we do optimization back then so that we can then extend it, because the rules that we're going to develop are not intuitively obvious, but they're really cool because once we do it, we can now apply it to all problems. So Calc 1, okay? You want to construct a rectangular fence with perimeter, let's call it capital P. P could be 100 feet, whatever you want, just pick a number. With the maximum area. So think of it like this. I have a certain amount of fencing material. Make it 100 feet if it makes it easier for you to conceptualize. Now, I want to build a rectangular fence. Aren't there an infinite number of rectangles that I could build this fence out of that would use all 100? Great. So how do I derive the maximum area? So this is the first problem I always do in Calc 1 for optimization to kind of get us started, because this is the first time you've actually done a calculus problem with what's called a constraint. Because if I just said maximize a function, well, I take a derivative, I set it equal to 0, life is good. But I have a constraint. In this case, I have a constraint on the perimeter. So let's start simple. I have a rectangle, let's call that x, let's call that y. So I want to maximize, what's the area of this rectangle? Subject to, what's the perimeter of a rectangle?
2x plus 2y.
2x plus 2y, good. Subject to 2x plus 2y equals capital P. That second statement here, this is called my constraint. All right? So for every constraint, you'd get a different final answer, but you still would approach it essentially the same way. Everybody go with that? So, well, I can't just start off by taking derivatives because this is Calc 1. I can only have one independent variable. This is the thing I'm maximizing. I'm not maximizing this. This is constant. I'm maximizing this. So what I really like to do is have area be a function of one variable. How would I do that? Go back to the constraint and solve either x or y in terms of the other one. Does that make sense? Yeah, okay. I do that in remedial algebra. I'd solve for one. Well, most of us like functions of x, so let's write y as a function of x. So 2y would then be p minus 2x, so y would be half p minus x. Now remember, p is a constant. P is not a variable. So now I can say area as a function of x is x times 1/2 p minus x. Now I have a function of one variable. I'm going to go ahead and distribute. That makes it a little bit easier. 1/2 p x minus x squared. Now, the only way you can maximize or minimize a function is to take the derivative, find out where it equals 0, and so on. Okay? So let's do that next. So a prime of x would be what? Anybody? 1/2 p minus 2x. I want to set that equal to 0, and that would happen when 1/2 p equals 2x or x equals 1/4 p. Okay, I have a critical value at x equal 1/4 p. Is that automatically going to give me the maximum or automatically going to give me the minimum, or do I have to kind of test it somehow or another? Yeah, this is not a joke. A lot of times when we were in calculus and you're asked to find extrema or find the max or min. We took a derivative, set it equal to 0, there's our max. It might actually have been the min. Or worse, it was a point of inflection that gave me a horizontal tangent. Ooh. And I identified it as a maximum or minimum when it actually was neither. No, just because the derivative of 0 doesn't mean it is the maximum or it isn't. I mean, it says that's probably where the maximum is coming from. Now, because I have a constraint, things are a little bit different. We like constraints in this situation because then we can use something called the extreme value theorem. Now, lest you forget, you take a derivative, you set it equal to 0, you solve. You can use the first derivative test to determine where the derivative changes from increasing to decreasing. That. I can use the second derivative test to say, am I concave up or concave down? I know my dean coming around and getting on me. I actually got a nastygram last semester, general nastygram, that there were faculty in the math department, I don't know who they would be, that said that they told the students they didn't have to wear masks anymore. I think that was a little silly because I don't think anybody did that, but apparently the dean came around and entire classes had no masks. Yeah, so we all get the same nastygram when that's the case. So first derivative test, right? I look at the interval, increasing, decreasing, all that stuff. Second derivative test, I say, is the second derivative concave up or concave down with this. But the extreme value theorem, when you can use it, is usually the simplest. The extreme value theorem, if you remember, says if you have a closed interval, all you have to be is differentiable on the interval. This is differentiable, it's a polynomial. Then there is always an absolute max, and there is always an absolute minimum, and they can only occur at critical values and at endpoints. Does that sound familiar to anyone? That, of all the theorems you learned in Calc 1, that's in the top 3 of importance because in application, it is the single most important theorem that you use because it's the one you use the most often. When there's a constraint, rather than doing first and second derivative tests, you just look at it. So, where's my constraint? Oh, P is a value. So doesn't that mean X is bounded? Let's just say P was 100. Then X can't be 1,000, can it? In fact, if P was 100, what's the biggest X could be? If P was 100, what's the most X could be?
49, 29.
No, 50. No, if you said 14 point something, then that would mean Y had an infinite range. No, X could be 50. Now, it'd be a pretty boring fence if I took two 50-foot portions of the fence and just stuck them side by side. We agree that'd be boring. But does it defy any laws of physics or anything else? No, it wouldn't be a very good enclosed region, but it would be possible. So X can't be negative, but if X were 0, then Y would have two 50-foot portions. So is it true that X has to be between 0 and 50? Do you agree with that statement? And by the way, anytime you have an interval, you would prefer the interval be a closed interval. If the interval is not closed, if X showed up in a denominator, then it couldn't be 0, obviously. We prefer a closed interval because then that means I have endpoints. So the extreme value theorem says all I got to do is take that value, which was my critical value, that value, and put them into there and see what I get. And here's the beauty. If I take either the 0 or the 50, or I should say, in this case, I said 50 for a 100-foot fence. It's a P-foot fence. So therefore, what's this? Half P. We'll be more specific. If I take 0 and put it in here, I'm going to get an area of 0. Do you agree? If I put 1/2 P in here for X, I'm going to get an area of 0. Because that means I have two 50-foot slats either sideways or vertically. And if I put 1/4 P into this, I get some positive number. In fact, what would I get if I put 1/4 P? I'd get 1/4 P times, 1/4 P, which would be 1/16 P squared. But more importantly, if X is a 4th P, then what's Y? 1/2 P minus 1/4 P, and oh my goosh. The maximum volume will come from a square. Mind-blowing, or is that kind of an oh duh? Yeah, it's more of an oh duh, but we just proved it mathematically. Yeah, we knew the answer was going to be a square, but how would we show that? So we just proved that the maximum area will come when this thing's a square. Great. Now, it's not always going to be that simple. That's why I say we start with this one. Now, everything we did was true. Everything we did was correct. Our issue would be, what if we have more variables? what if this is now a three-dimensional thing? Then I can't do all of this. And we could try to use what we did yesterday by doing the Hessian and all that stuff, which is great if I have a function over the entire xy plane. But if I have a constraint, you see, that's not going to work. So we need to tweak our approach to allow the constraint if I'm in a higher dimension. So that's what I'm going to do next. We're going to develop something. And this is not intuitively obvious, the development. Now, I think I did some of this, a version of this before already. So here's the thing. I'm going to give you a constraint. Okay? What I want to do, the xy plane, I'm going to give you a constraint. My constraint might be, you know, I have to be, y has to equal x squared on my constraint, or y has to be 2x plus 5, it's a line. I'm going to give you a constraint in the xy plane. It could be x squared plus y squared is 25, right? That would mean I have to be on the circle. I'm going to give you a constraint, which means whatever the answer that I'm looking for must be on that curve. But when I give you a constraint, I want to write it in the form g of x comma y equals 0, meaning I want a level curve. So if I just gave you simply the equation of a line, okay, here's my constraint, you know, how do I do this? Well, of all the things you do, that's probably the simplest one. If this was my constraint, how do I make it into a g of x y equals 0? I'd say, let g of x y be what? How about 2x minus y plus 10? Would that work? Yeah, you just throw everything on the same side. That's it. Oh, okay. Now, on the previous quiz that you guys turned in and you were doing partial derivatives to figure out your, instead of implicit differentiation, the trick was create a new function by throwing everything on the same side. Now you have a function of more variables. But the common mistake people did was they said, and when I do that, that thing now equals 0. No, that's not true. When you throw everything on the same side to create the three-dimensional function, if you set it equal to 0, now you get back to your original thing. You now have a level curve. You now went from 3 dimensions back to 2 dimensions. You don't want to set it equal to 0, well, ever. Why? Because if I write now this equals 0, then every derivative I take will have to equal 0 because I'm differentiating 0. That's bad, by the way. If I take my new function and set it equal to any constant, then all derivatives means I'm differentiating the constant. And so your final answer to every question would have literally been 0 over 0 for every problem that exists. No, 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 no. We create a new function, and this is a level curve of this, but this has an infinite number of things. So I create something like in that nature, because now I have a function of 2 variables so that I can do certain things, okay? So we start with this constraint. So let's suppose the graph of this, and here's the cool thing. This doesn't have to be a function in the xy plane. I said it could be a circle. All right, so then I'd make my g of xy, you know, x squared plus y squared minus radius squared. Right, I can do that with anything. That's the nice things. I have license. So I drew myself a little picture here. I've got some, here's my constraint. This is just something on the xy plane that I'm going to throw everything on the same side, and I'm going to call this g of xy. Now, this is my general, but I want this to equal 0 to produce this curve specifically. See, now is when I do want to say, and this equals 0 because this is the level curve. So if I said, and this equals 0, now I have this specific level curve back again. Okay? So I create a new function because I'm going to differentiate that new function at some point. So I've got this. Now, we already know how to create a vector value curve. Okay? So if I just said, let's call this R of t. That would mean that I need, in every situation, x to actually be x of t and y to be y of t in order to do this. Ah, okay, so this therefore would be x of t, so I'm going to have to erase this, a little too tight. We're familiar with this. This is not new. We've been doing this for quite a while now. I have a vector value curve that we know will describe this curve. Even if this curve's not a function, I still know I can use a vector value thing to describe this. One of the advantages of doing it this way, I now only have one independent variable. That makes derivatives a heck of a lot easier in the long run. Now, let's suppose that there's a place on here of particular interest. Maybe the answer to my question is going to be at some particular ordered pair, let's call it x0, actually move it over here, x0, y0. This is a particular point of interest. So when I'm maximizing or minimizing, maybe that's where the answer is going to occur. So I'm interested very specifically in this vector value function. So that would mean, what would I call this though? Oh, if that's the case, then doesn't that mean that x0 would be what? X of t0 for some value of t0, and y0 would be y of some value of t. So there's going to be a particular t that produces the x and y because we've... All right, so that means that this would be what? R of t0. Okay, that makes perfect sense. So R of t0 would be R of x of t0, y of t0, and that's what we're going to call x naught, y naught. Okay, so far so good. Haven't actually done anything, but I'm labeling everything. Now, let's consider that point of interest. I have a tangent vector that I could draw from here. And we'll assume we're moving this way. It doesn't really matter, but let's say we're moving this way, mostly because it's easier for me to draw my picture. So this would be dr dt evaluated at t naught. Okay, I should say at t equals t naught. I want that specific one. And there's also going to be a gradient vector that points this way. We'll call this the gradient of g. Okay? Now, we know that the gradient is orthogonal to the curve. And I'm going to go back and show you that again, in case we forgot that. We know the gradient is orthogonal to the curve. It goes in the same direction as the unit normal. And I think I did this in one of the earlier videos. I'm going to kind of redo it now because I need the result for what we're doing today. None of us have an issue with the velocity vector. We know it's tangent to the curve because the unit tangent's the unit vector in that direction. The gradient being orthogonal, I did show that on one of the videos, but that's not, to me, that's not intuitively obvious. But we need that, so I'm going to kind of re-show you that one in a moment. But I'm going to do it from this point of view, from this vector point of view. Okay? Now, here's the thing. I haven't even got a function to maximize yet. I don't have any problem yet. What I'm trying to do is establish a relationship between the vectors that we're coming up with. So let's start with this problem. I'm going to rewrite g of xy as g of x of t, y of t, so that everything matches. Okay? Because we're actually saying the vector valued function will produce all my points. Okay? So if I have this, what I want to do is differentiate both sides of this with respect to t. Okay? So let's see. Here's how we do it. We want to go d dt both sides. All right? So on the left-hand side, how do I differentiate? How do I differentiate with respect to t? So we're actually going to differentiate. Well, t is an independent variable, isn't it? But x and y would be dependent variables. So this is going back to the chain rule. Do you guys remember the video I did where I had like your little arrows, where things go? It's not life and death if you write partial and it's ordinary, or you write ordinary and it's partial. It's not going to mean you did the derivative wrong, but it's good to know which ones are which. G sees two variables. It sees x and y. G sees two variables. Okay? So any derivative I take of g has to be a partial derivative, doesn't it? Because it has two choices. X and y each see one variable. So any derivative I take of x or y has to be an ordinary derivative because they only see one variable. You with me? That's actually how it works. So I have the partial of g with respect to x times dx dt. Okay, this goes back to my picture, and I'll remind you what the picture looked like. We had, kind of went like this. I had, so it's partial ordinary, partial ordinary, and they get added. Now, what is this quantity? This is the derivative of g. Okay, this is, I guess I'll write it right here. This is dg dt, if you will. Okay, that's what it is. But I'm differentiating something that now very specifically equals 0. So can I, that's why I said before, when you're creating a new function in general, don't set it equal to 0. I'm creating a new function, but I want the level curve of that one. I very specifically want this to equal 0, so now when I'm done differentiating, I just differentiated 0, didn't I? Okay, now look at the right side. In the videos that I showed you, I do the same thing. I have something times something plus something times something. That feels a lot like what? Dot product. Something times something plus something times something feels like a dot product. In fact, it's actually a dot product. Can you tell me exactly the vectors that I dotted? Yeah, that's actually the easy part. Wouldn't that be this? Does that make sense? It's like, oh yeah, that's an O-dub. They're sitting right there in front of me. But those are two hugely important vectors. The one on the right, that's easy. This is dr dt. I know that one, that's the velocity vector. That's that vector right there. And what's this one? I took a function, I made it into a vector by taking partial derivatives. Starts with a g, ends with a radiant. Gradient, that's the definition of the gradient vector. So this is the gradient of g, dotted with that. And it all equals 0. Awesome. Piece of cake. By the way, since it all equals 0, this actually is the formal mathematical proof that the gradient vector is orthogonal to the velocity vector. But because the velocity vector is tangent to the curve, that proves that the gradient must be normal to the curve. Because we know the normal and the tangent must be, not unit vectors, but just the normal direction. This is actually the simplest proof. And it's a little complicated. So it's like, cool. But we technically already knew this. You're right, we technically already knew this. So now I'm going to throw in the situation that we're after in the first place. I have a function that I want to maximize or minimize. I want to find the extreme. I just have some function out there. F of x, y, we'll fill in the blanks. It can be anything you want. And I want to find the extreme of this function subject to this constraint. Okay? There's no f in my picture. I'm not taking the picture because f is three-dimensional. F could be a circular paraboloid. I want to maximize or minimize some three-dimensional function subject exactly to this constraint right here. And the reason I needed to make this way rather than just y equals f of x kind of thing is because my three-dimensional function is a function of two variables. I therefore need a constraint that has the same look because I need everything to match up. The numbers of variables have to match up. Okay? You can't do a mismatch. I can't solve a three-dimensional problem with a two-dimensional constraint. I need my constraint to, look three-dimensional in general. So we have this. We know this. That's not an issue. The next piece of the puzzle in here. All right, so now what we want to do, I want to, for some given function, I want to find the extrema of some function f of x, y. You can say z equals, it doesn't really matter. I have some function I want to find extrema. Now, there is no guarantee that there's going to be a maximum and a minimum. But with a constraint, there is always something. There's always going to be one or the other. Now, in count 1, when I gave you a closed interval, we said there was always a maximum and a minimum, and it occurred at the critical value or the endpoints. That's awesome. That was great. But this is infinite, isn't it? This isn't a small closed piece of a curve. This is a curve that goes forever. Okay, so first of all, I'm not going to have the same rules. I'm not going to have endpoints. I'm going to have a constraint, but I'm not going to have endpoints. So therefore, when we're doing this problem, we're going to be guaranteed an extrema. And we might actually have two. we're going to be guaranteed an extrema, but we don't know ahead of time if that extrema is going to be a max or a min. I'm going to show you how to figure that one out. The figuring out if it's a max or min is trivial. But we're guaranteed an extrema, we just don't know which one. Okay? You with me so far? So I want to find any extrema of this, oops, subject to that. Okay? All right. Now, let's go back to this picture. Let's suppose now I have my f of xy, which is some surface. You know, maybe it's out here. Let's suppose, just to make it easier because of my picture, let's suppose the extrema happens at x naught, y naught. Okay? Let's suppose it happens. It's going to happen somewhere. We'll call that the place it happens. All right? So in other words, suppose f of x naught, y naught is either max or min. Okay, I have an extrema, it's going to happen x naught, y naught. We would actually do the calculation to determine it. Okay, but I want to show you the relationship so we know how to figure it out. Okay, now I'm going to create a new function. Right now it's just f of xy. I'm going to say, let's create a new function, let's call it capital F of t. And we're going to replace that x and y in our little f as x of t and y of t. We know this is legal. Okay? I can do this for anything. It doesn't matter. And let me remind you of how simple this is in general. You did this at the end of Calc 2. I have y equals x squared. I want to parameterize this. Parameterization is as simple as doing something like this. All right, let x equal t, then y equals t squared. I'm done. Now x and y are both functions of t, and so therefore everything I use is going to be a t or a t squared. That's how easy parameterization is in general. Pick one of your variables to be t, and then the other one is whatever the function of t is. But I've just parameterized it. I no longer have an x or a y, now I just do t's. Am I going to still do this? Yeah. I can do this for anything, but I can do this for things that aren't even functions. If you remember when you had a circle, you said, let x be cos t and y be sine t. Oh, then x squared plus y squared was 1. And that's, you did certain things that made it easier. And the beauty of parameterization is I can take things that are not functions in xy world, but make them functions of t. That's one of the benefits of doing that. Then it makes differentiation and things maybe easier. So I'm just going to say, we're going to call x x of t and y y of t. Boom. So this is what I'm dealing with. I'll just call it this for convenience. But you notice I call it big F because big F is now a function of only one variable. Okay? Understanding that the maximum or minimum is going to occur very specifically here, or in other words, at t naught. So here's what I know for a fact. I know that f prime of t naught is 0. Why? Because this is an extrema. Okay? And x naught is x of t naught. Y naught is y of t naught. We already said that. So this would just simply mean I have, so let me remind you. So f of t naught is f of x naught, y naught, using the notation we've already established. This is really, really important because that's where my extrema is going to occur. So what I want to do is, in general, I want to take d dt of both sides of this. Okay? Not d dx, d dt. So when I differentiate both sides of this, I will get f prime of t on the left. That's easy. What is it on the right? Oh, chain rule again. Okay. F sees two variables, so the first derivative is going to be a partial. So it's going to be the partial of f with respect to x, but then x only sees one variable, so this times dx dt. It's just good form to have the right kind of derivative there. Again, it's not going to kill you if you partial versus ordinary if you mix them up, because it's still going to give you the same answer. But part of the problem with mixing them up is dr dt is involving ordinary derivatives, so I really shouldn't see partial derivatives in that answer. So this ordinary derivative is kind of important. because we know it's going to show up in the drdt later, plus partial of f with respect to g times dy dt. Okay, great. This is seeming really familiar. Didn't we just do something like this with g? Doesn't that look like a dot product again? Yeah, okay. Well, what dot product is it? It's partial of f with respect to x, partial of f with respect to y, dotted with dx dt, dy dt, and that clearly is the gradient of f dotted with dr dt. Okay, now, in general, this is not zero. No, this is not zero. This is zero. So if I said, what if I do the gradient of f evaluated at x naught, y naught, oops, and I dotted that with dr dt, evaluated at t equal t naught. So I'm very specifically dotting it with everything that occurs at the interesting point. Is this quantity equal to zero? Yes. And this is where it's huge. At the point in question, at the place where interesting things happen, at the place where I'm going to get my maximum or minimum, the dot product of the gradient of f and the velocity vector, if you want to call it that way, are orthogonal. These guys are orthogonal. But didn't we already prove that these two are orthogonal? Let's think about this for a minute. I have a plane, we'll keep it simple. This wall is orthogonal to the floor. Do we all agree with that? That wall over there, which is a different wall, is also orthogonal to the floor. Tell me about those two walls.
They're parallel.
They're parallel. I'm in 3D. I have a vector that's orthogonal to a vector. Then somewhere else I have another vector that's orthogonal to the vector. And these two are on the plane. Don't these two then have to be parallel? What have we just proved? We have just proved that the gradient of g and the gradient of f are parallel. Why is that important? Because parallel vectors are scalar multiples. Is that important? Yeah, that's how we're going to solve problems. They're scalar multiples. And by the way, this is true if I have functions of 3 variables also, because I use a level surface instead of a level curve. Well, how does that help me in general? Remember, I said this is true at the x naught, y naught in question. It's not true for all points. It's true for the point that I need. So I start by creating the situation where they're parallel, and then I find that value. So we write it like this. Here's the problem we're going to solve. We start the problem, and we write it like this. Okay? This is the Greek letter lambda. L-A-M-B-D-A. The Greek letter lambda. Some of you may or may not have seen that before. Lambda is called the Lagrange multiplier. Okay, so you saw that name somewhere. I'm a big fan of bringing up all the calculus you ever see in your lives. I mean, if you were in my Calc 1, we proved the fundamental theorem of calculus by using the garbage pit scene from the original Star Wars, right? So as delta x approaches 0, what's happening to all the people? Yeah, they're all going to get squished to become one with the wall. I actually use that to prove the fundamental theorem of calculus as you're taking that limit. Everybody understands cat in the hat. You guys remember cat in the hat? Who are his little minions? What were they called? Thing 1 and thing 2. You guys may not realize it, but cat in the hat was your first introduction to 3-dimensional functions. Thing 1 and thing 2 were clearly independent variables, and that's what they were trying to get you ready. There is calculus in every aspect of life. You just weren't ready for it necessarily, right, at the time. You know, how did you guys learn quotient rule in my class? Well, of course, Snow White and the Seven Engineers. That was the song they sang every morning on their way to work, you know. Ho-de-hi minus hi-de-ho, all over, oh-ho, and then they do that annoying whistling thing, and that is exactly the quotient rule. Yeah, there's calculus in everything you do. Well, it turns out there was a very famous band in the 80s and 90s. You guys may have seen them. They had the really long beards. You guys know who they were? Anybody heard of ZZ Top? There you go. Go look them up on YouTube. One of their biggest hits. They sing a song about three-dimensional optimization in calculus. I kid you not. You can't tell what they're saying most of the time. You guys have probably heard the song, how, how. How many have heard that? Go look it up on YouTube. They sing a song, it's called Lagrange. And the entire song is about three-dimensional optimization of functions and stuff. You probably won't be able to get it all because they kind of mumble all the words. I put it together myself, what they were singing about. It's beautiful. There's a partial derivative here and solving an equation there. Yeah, well, at least in my world, that's what they're singing about. But it's, classic song. It's a rock and roll song about calculus. But then again, if you've been around me long enough, you know I'll make everything at some point about calculus, right? But anyway, we're going to solve a problem. The point of a Lagrange multiplier is not to solve the problem. It's to set up the problem that you can now actually solve. So let's go back to the problem we started class with. Now, the problem we started class with was an easy problem. I mean, that was an easy problem in Calc 1, but I want to look at it from a different point of view. So here's what I want to do. We want to maximize area. Clearly, area is a function of x and y, isn't it? Because we said we're maximizing area equals xy. And what were we subject to? 2x plus 2y equals p. This is the problem we started class, and then we had to solve for a variable substitute, and everything we did was true and correct. Let's do this, though, from a three-dimensional point of view. Let's not solve for a variable and substitute. Let's just go with it. So the first thing we're going to do is create our g of xy. So we're going to say let g of xy equal, how about 2x plus 2y minus p? Space here. So now, the gradient of A is what? What's the gradient of A? It's y comma x, because I'm taking the partials. So y comma x. What's the gradient of G? 2 comma 2?
Yeah.
So here's what we want to do. So here is the problem we're going to solve. We want to solve the following. The gradient of the function that I'm trying to find the extrema of is equal to a scalar multiple of the gradient of my constraint. That's always the way it works. Now, here's the interesting thing. Lambda is an unknown. But we rarely seek to find lambda. If it falls into our lap, by the way, if lambda equals 5, just like right there, I didn't have to do any work, I'll take it. But we don't really care the value of lambda, we care what lambda does to the relationship. You see, doesn't this mean that y equals 2 lambda? Because I have an equal sign between these two. And doesn't this mean that x equals 2 lambda? I don't care what the value of lambda is, what does this tell me? That y equals x. Because both x and y were equal to 2 lambda, they must equal each other. Oh, okay. Now, I need their values. How do I figure out the values now that I've established that relationship? I go back to the constraint. If 2x plus 2y equals p, and y equals x, then doesn't that mean that 2x plus 2x equals p? So 4x equals p, so x, which equals y, equals 1/4 p, which was our result earlier, but from a very, very different point of view. Now, I found an answer. We already know that this was maximizing area, okay, but I need to prove it maximizes area. How many ordered pairs of x and y make that statement true? I should go here. How many x's and y's make this true? In other words, how many different shaped rectangles could you make with the perimeter of P? At least like 5, right? Maybe even 7 if you really think about it. Or more? A lot, good. There's a lot. We all agree there's a lot. How do I know this is the maximum? Well, here's the beauty. I said this is going to produce an extrema, which means the area I get from this answer is either the most it can ever be, there's no situation that's bigger, or it's the least, there's no situation smaller. It's an absolute, it's one or the other. So all I need to do is pick one ordered pair, x and y. Pick any ordered pair, x and y, that satisfy this constraint. That's all I have to do. Okay? And my favorite ordered pair always involves as many zeros as I can come up with. Because you're less likely to, don't say, well, how about if I pick x to be 1/7 p, and then we figure out what y would have to be. Why not pick x to be 0 and then y to be half p? Or pick y to be 0 and pick x to be half p. Does that satisfy this equation? Yes. It makes more sense choosing something with zeros because the algebra is easier. So right now, here's what we got. Based on this, the area of 1/4 p comma 1/4 p equals 1/16 p squared. Okay, because that's what we said our x's and y's were, and then we put them into the area. I believe it's the biggest, but I have to prove it, and the way I prove it is to find any ordered pair that satisfies the constraint. It has to satisfy the constraint. So I can't use 0, 0. That doesn't satisfy the constraint. Can I use 0, comma 1/2 p? 1/2 p? All right. So let's use 0, 1/2 p. All right. So then what is a of 0, 1/2 p? Well, that's 0, which is less than 1/16 p squared. What this means in simple English is, of the infinitely many combinations that satisfy this, every single one of them would have produced an area that was smaller than our answer. Had the inequality gone the other way, then it means that of the infinitely many choices, every one of them would have exceeded our answer. So that makes it really obvious that our answer in this case must be the maximum. But you only have to test one value. That's the best part. You only have to test one. Well, in Calc 1, didn't you do the same kinds of things to figure out max and min? You tested something, right? And if your value is bigger, okay, mine must be a max. If my value is small, it must be a min, that kind of thing. So it's kind of overkill to have used Lagrange multipliers on this problem because we already knew how to do it. So let's do something that's a little bit higher level now, okay? I had to start with something where we already knew the answer because it does make it easier to justify it then. So, let us find the extrema of f of xy equals 2x squared minus 4y squared subject to, hold on, what did I choose? Can't read my own writing. Oh, subject to y equals 2x plus 7. So I have some three-dimensional surface. Now here's an easy way to think about it. Whatever this surface is, on the xy plane, y equal 2x minus 7 is a line on the floor, isn't it? But if I think of that as three-dimensional, wouldn't that make it a plane in 3D? Does that make sense? Oh, because the z. So I have my three-dimensional surface, and I slice it with this plane. Now I'm thinking really of a two-dimensional curve, aren't I? Will that have either an absolute maximum or absolute minimum? Well, if it's subject to being on there, it will. It won't necessarily have both. Most of the time, you won't get both. Most of the time, you get one. That's one way to think about what I'm suggesting here. Okay, is to think about it as slicing a three-dimensional thing. So, very first step, I need to create a three-dimensional function for my constraint. So we will let g of x, y equal, it does not matter which way you subtract. So I'll do 2x minus y plus 7. It will not change your final answer. Just make sure you subtract correctly. The algebra, you don't have any control over the level of difficulty of the algebra. More often than not, you're going to get, lots of fractions and different things. And don't assume you did it wrong because you don't get happy numbers. Most of the time you won't. I reverse engineered this one so you would. So my first step is, what is this? Let's do these together. Okay, so what is the gradient of f? You don't have to think too hard. 4x.
Negative 8y.
Negative 8y. Okay. And what's the gradient of g? 2 negative 1. We like things like this. We love it when we have constants. We don't like it as much when we have variables in each position because sometimes it makes it more work. Okay, so 4x negative 8y, I'm going to set equal to lambda times 2 negative 1, and that gives me two equations. It gives me 4x equals 2 lambda, and it gives me negative 8y equals negative lambda. Now, something that you may or may not remember, but to get a unique solution to a system of equations, that is a system of equations. To get a unique solution to a system of equations, I have to have exactly the same number of variables as I do equations. A simple way to remember it, if I have more variables in equations, then I'm usually going to get an infinite number of solutions. Okay? If I give you one line, I have 2 variables. If I give you 2 planes, I have 3 variables. So if I gave you that wall and that floor, and I said how many solutions, be infinitely many along that line. Oh, but if I gave you that wall, the floor, and that wall, now there's only one solution, the corner. So I have to have the same number of equations as variables in order to have a unique solution. It appears there's a dilemma here. How many variables do you see in this? You see 3. Oh, how am I supposed to do that? Well, because there actually are 3 equations. These 2 and this one. Your constraint that you were given is one of the equations, and you're always going to use the constraint because once you figure out a relationship, you're going to use the constraint to figure out the actual values. So you actually do have enough equations and variables. So I am not interested in the value of lambda, but how am I going to figure this out? Well, 2 lambda negative lambda, what if I multiply both sides of this by negative 2? Would that be a good idea? Because then the right sides will be the same. And if the right sides are the same, then the left sides would have to be the same. So if I do that, I've got positive 16y equals 2 lambda, but 4x also equals 2 lambda. Therefore, 4x must equal 16y. That's a good thing. Because that's very, very nice to work with. Okay, I don't know the value of x and y, but I know that 4x equals 16y, so therefore x equals 4y. No matter what my final answer is, x is going to be 4 times the value of y. Now, how do I figure out what x and y are? I take that, and I go back to here. Okay, since x equals 4y, I will replace x with 4y. That's easier. So now what have I got? I've got y equals 2 times 4y plus 7. I'm replacing the x with 4y. So y equals 8y plus 7, or negative 7y is 7, so y is negative 1. If y is negative 1, then what is the value of x?
Negative 4.
So x is negative 4. Well, that wasn't too bad. By the way, could I figure out the value of lambda now that I know what x and y are? Sure. Is it going to matter? No. It's not going to matter. You're not going to worry about it. But sometimes I said you can find lambda first and it makes it easier, but I'm not seeking the value of lambda. Now, one thing, lambda can't be 0. Because if lambda is 0, then you're saying that the only solution is to not have an actual multiple, to have 0 vectors. No, that won't work. So, and the reason I point that out is because you are going to sometimes manipulate the lambdas. maybe move them around, multiply them, divide them. Lambda can't be 0, because if lambda were 0, then the only solution would always be the origin. And that's not really a very viable situation. Okay, so I haven't got the answer exactly. I now need to say, what is f of -4, -1? Let's calculate that value. Did I say x is -4, y is... Did I say that backwards? Did I get that right? Y is -1? Yeah, okay. So I don't want to mess that up. So what do we get here? Anybody got a number?
28.
28. Well, clearly that's an absolute, I don't know. A common mistake that people make is they look at that number and go, oh, obviously that's a... Do you automatically know that's a max or a min because of it? I have fun with this. I'm notorious for doing things like this. That might be an absolute maximum. It might be an absolute minimum. What if I said, just for fun, plus a bazillion? Understand, bazillion is the largest number there is. It's like 1 short of infinity. If I put plus bazillion, now I have an astronomically large number, which doesn't change whether it's a max or a min, by the way. What if I put minus a bazillion? Now I have an astronomically negative number. And that still doesn't, adding the constant to the end doesn't change the max or min. My point being, you cannot go by the size of the number. It will never work. You will guess, well, yeah, actually, I shouldn't say it'll never work. If you use the size of the number to come up with your conclusion, how often are you going to be right? 50% of the time, because in other words, you're absolutely guessing. You can't use the size of the number, because if I arbitrarily added or subtracted a number, that would greatly influence you. Yet it wouldn't change your answer. So what we do instead is we pick a value, or excuse me, pick an ordered pair that satisfies this constraint. Is there an obvious one? I have a favorite. See if any of you have the favorite, my favorite. What would you choose?
0, 7.
0, 7, because if I pick x equals 0, then y is 7. If I pick y equals 0, then I got to solve for x. Pick x as 2/3, and then, no, don't do that. Pick one of them to be 0, then the other one's easy. So how about we use 0, 7? You all agree? So I'm going to use 0, 7. So then, what is f of 0, 7? 0, 7 is a point on the constraint. Therefore, it's a legal test. So if I plug 0, 7 into the f function, I'll get what?
196.
Positive or negative?
Negative.
Oh, that's important. And that is smaller than 28. Therefore, this is the absolute max. That's it. That test is so simple, and it is always simple. The test, because I chose any point that satisfied the constraint, okay? If I have, let's suppose we did a 3-variable problem. Okay, I have an x, y, and a z. Then my philosophy is pick 2 of them to be 0, right? And then figure out what the third one is. It's just the least amount of algebra required, because this conclusion is going to be the same regardless of what ordered pair you chose, as long as that ordered pair satisfies the constraint. Okay? So far, so good? That wasn't too bad, was it? You're just like, I wouldn't even know how to solve this problem otherwise. Yikes. Let's do another one. How about let's see. Whatever this is, I want to find either its absolute max or its absolute min. Again, there's no guarantee that I'm going to get both. I'm guaranteed to get one. Now, let me back up a second. What if What if in the process of Lagrange multipliers, we clearly get two solutions? Well, that's your favorite problem, because one of them will have to be the absolute max and the other will have to be the absolute min. Well, how do I test it? Well, one was bigger than the other. And remember, if they both satisfy the constraint and one is bigger than the other, then the bigger one has to be the absolute max, the smaller one has to be the absolute min. You actually like it when you get two solutions because the test is built in, because you already have 2 points you're checking out. Now, I don't know ahead of time when you're going to get 1 or 2. That's not even important. If you get it, you get it. Don't worry about it. But this is a trickier problem because it technically means now I've got to solve for 3 variables. And you're not going to be able to figure this out in your head or try to draw a picture. That's really not going to be very useful. So the first thing I need to do is create a new function. Okay? I need a g of x, y, z this time. Now what do you suppose I should call it?
W.
What should this be?
X squared plus y squared minus z.
Yeah, I'd probably go that way. You could, again, it does not matter what order you subtract. All that would mean is the value of your lambda at the end would be the opposite sign, but it wouldn't change your final answers. Subtracting in a different order doesn't make your answers negative. No, it means your lambda would be the opposite sign, but you're still going to get the same values. And since we're not finding the value of lambda most of the time, that's really not important that it would be opposite sign. All right. Certainly the first part of every problem is kind of self-navigating, right? That's my first step, is to create a function. Now, why did I need to create this new function? Because this guy's got 3 independent variables, and I'm going to take its gradient and set it equal to a multiple of this gradient. Therefore, this gradient has to be the same dimension. Okay? You can't set a 3-dimensional vector equal to a 2-dimensional vector. That doesn't work. So they both got to be the same dimension, and I can't go down a dimension, but I can easily go up by doing this. So, the gradient of f is what?
4, comma, -6, comma, 2.
And the gradient of g is
2x, 2y, -1.
2x, 2y, -1. Okay? So, 4, -6, 2 equals lambda times. Now, this time the lambda is going to be on the same side as the variable. In all actuality, does it actually matter which side I put lambda on, in actuality? No, because lambda can't be 0. So it doesn't matter which side I put on. If I put on the other side, then calculating its value would just be the reciprocal. It does not matter what side you put it on. So most people tend to do gradient of this guy equals lambda times gradient of constraint. Just, you always do things in the same order, it's easier. So this says that 4 equals 2 lambda x, -6 equals 2 lambda y, and 2 equals negative lambda. Oh, I got a freebie here, don't I? And my freebie is we know the value of lambda. We didn't need to do anything to find the value of lambda. It's sitting right there. Now, can the value of lambda help me? Yeah, because if I know the value of lambda, will it be easy to find x and y? Yeah, so we like this one. We didn't seek to find the value of lambda. Understand that. It just fell into our lap. Okay? So this, I'll put the arrow here, this says that lambda is -2. So going back to here, now I have 4 equals, if lambda is -2, then 4 equals -4x. And this says that -6 equals -4y. Okay, so therefore x equals -1, and what is y equal?
3/2.
+3/2? How am I going to figure out z?
Go back into the original equation.
Yeah, actually, z is going to be kind of simple, isn't it? It's just, I just stick them in there. So what's the value of z then? Z is going to be the square of -1 plus the square of 3/2, and that's what?
13/2.
13 over 4, beautiful. All right, so something interesting is happening at the point -1, comma 3/2, comma 13 over 4. So now what we need to do is find f of -1, 3/2, 13 over 4. I need to find this value, and I just simply plug it into there. So this is the easy part. So let's go ahead and find that, everybody. Hopefully we all agree. That's always a good thing.
-6.5, or negative 30 over 2.
So what did you get?
Negative 13 over
You got
2.
negative 13 over 2.
Yes.
Okay, I thought you said 13 over 2. Does everyone agree with that? Negative 13 over 2? Well, obviously, because that's negative. I don't know if anything's obvious. Okay, so this is a freebie. Can you give me an ordered triple that satisfies my constraint?
0, 0.
0, 0, 0.
How about 0, 0, 0? And believe it or not, if I ask this on a quiz, most people do things like, well, 1, 1, 2. That works. That's a great choice. Then I'll get people to go 2, 4, 20. But I'm inclined to, if x and y are both 0, then z is 0, I'm inclined to go 0, 0, 0. It's just harder to mess that one up. Now, you can't choose your variables to be 0. You solved for z, and z was 0 when x and y were 0. Okay? So, f of 0, 0, 0 equals what?
0.
0, which is greater than our answer. Therefore, our answer is the absolute minimum. That's it. I don't have to do anything else to prove that. Had you chosen, let's just say for fun, you decided to go with, 2, 4, 20. You're just being silly here. Okay, you used 2, 4, 20. What is f of 2, 4, 20, please? 8 minus 24, that's negative 16, plus 40, that's 24. Which is still bigger than negative 13/2, correct? My point is, it would not have mattered what order triple you chose as long as it satisfies the constraint. So always go for something that's really easy to work with. Yes?
In this optimization, is it always going to be absolute, or will there be times
Yes.
it's local?
There's no such thing as local extrema. Now let's go backwards one step, calc 1 again. When you're using the extreme value theorem, we know there's an absolute maximum and minimum if it's a closed interval and that was differentiable. The reason it has to be differentiable, you can't have holes and breaks and weird stuff, okay? In fact, technically, you really only have to be continuous, to be honest. So as long as you don't have any breaks in the graph, really, and you have endpoints, there's guaranteed to be an absolute max and a min, and they could only come from critical values for endpoints. Now, that means when you were doing extreme value theorem, this always confuses people at first when they're first doing this. Let me erase some of this. And so I'll usually choose problems that have lots and lots of critical values. And I'll say, okay, here we have a graph. Maybe my graph is doing this. Just have some fun. I got a graph that's all over the map. But my interval that I chose, let's say my interval went from here, to here, okay? That's a local maximum for the function, but it's not a maximum in my interval. That's clearly the maximum in my interval. And if these were the same height, then remember, the minimum would be the y value. So I'd have a minimum. And the minimum came from a critical value, the maximum came from an endpoint. So what do I do with these guys? Nothing. Because I wanted the absolute max and min over my interval. So we don't even bother with the locals. That's where things are a little bit different when you had a closed interval. If I said, consider the whole function, okay, then you'd say local max, local min, absolute min, absolute min. You do things like that for the whole thing. So in our case, it's a little different because this does go forever, but the Lagrange multiplier, remember, because of the situation we got, we now know there's an extrema. We know there's an extrema, but because of the being on the constraint, there are no local extrema on a constraint in this case. So if I don't do this, then I don't know if it's a max or a min, and you never want to guess. Okay? A bad question in some of the textbooks is it'll say find the absolute max or find the absolute min. Well, if I had asked you to find the absolute max, you got a problem. Why? As x and y grow without bound, and z ends up being the sum of their squares, think about doing this. How about if I replace this with this? As x and y grow without bound, these guys are growing much faster than these guys. Do you agree? So this is going to approach infinity. Oh. So there is no absolute max. So I can't maximize this. There is no ordered, there's no input that would give me a specific value. As x and y grow positively or negatively without bound, this term here is going to grow much faster than those because this is being squared. So that's why we don't say find the max or min, we just say find the extrema, because you don't know ahead of time which way it's going to go. If I said find the absolute min, we did. The absolute min is going to occur at -1, 3/2, 13/4.
So just like a real quick question on finding like the maximum and min. So almost every time when we do it, we want to try to find f of x or f of x, y, z, or whatever is equal to 0.
No, the constraint. The constraint equals it.
Oh,
Here,
constraint.
whatever I'm maximizing, I don't do anything with it. I find its gradient, but this is just the thing. This is the thing I'm working with. This is I fluffed the bed, the infinite bed sheet has peaks and valleys. If I said find the max and min of that one, that's what we did last week. That's the Hessian. But now I'm saying, no, I'm going to give you a constraint. I'm going to give you a constraint, and now it's find the max and min subject to this constraint. Oh, that isn't going to produce necessarily the same answers as the infinite sheet did. Because now that they have to be on the constraint, it might not even be a maximum or a minimum. Because now, remember, I said, think about it like now I'm slicing it, and now I'm looking at the level curve in a sense. Okay, let's do one more of this nature, a little bit more complicated. I have, let's say, this is always kind of a fun one. Let's suppose I have the following. I'm going to use a fairly simple one. I have x squared plus y squared plus 4z squared. And let's say that's, I don't know, about 48. Okay? Anybody know what this is? Yeah, maybe be more specific. It's circular. It's circular ellipsoid. Yeah, that's kind of cool that you can just tell me that without doing a whole lot of work. It's going to be flatter. Let me see if I can do this justice. Okay, it's a sideways egg kind of thing. Okay, that's terrible. I know that's not a good picture. I'm better with spheres. All right, here's what I want to do. I want to put a box in there. Okay, I've got an egg. I want to put a box, a rectangular box in there, a rectangular prism. So do I want the smallest box? Well, I could have a box of 0 volume if I just make it on the plane. No, I want the biggest box I can put in there. Huh. Now, think about it. I want to put the biggest rectangular box in there. So that means the vertices of the box have got to touch this, don't they? Well, how come? Well, it'd be like saying, let's work in reverse. I want the largest sphere that you could put in this room. Well, if your sphere didn't touch the floor, the walls, or the ceiling, then couldn't I put a bigger sphere in, one that eventually does touch? Does that make sense? If I just put a ball in the middle of the room, if it's not touching anything, how can it be the biggest? Because I can keep expanding. So I'm putting a box inside of this. The vertices have to touch the thing. That's kind of a no-brainer from that standpoint. Now, does it have to be centered at the origin? Actually, it does. Why? It's tricky, because that's centered at the origin. Oh, so if I try to push my box to one side, that's like saying I'm going to put the sphere in my room and touch that wall. But not, no, I need to center the sphere in the room if I want it to be the biggest sphere, because I have the most to go in each direction. So I want the largest rectangular prism. Is that prism going to be a cube, do you think? Probably not. If this were a sphere, would it be a cube? Yes, but this is not a sphere. So I need something, right? So let's go and try to, sorry, I need a different color here. Let me do my best terrible drawing here. So there's something in here that touches. How's that? Every one of these points is touching. But if it's centered at the origin, then there's going to be a point in 3 space, and that point would be x comma y comma z. On the other side, I'm going to have negative x comma y comma z. Underneath, I'm going to have x comma y comma negative z, and so on and so on and so on. You with me? Can you tell me the dimensions of the box then? Good. It would be 2x by 2y by 2z, because, in fact, let me give you a simpler analogy. This will make it easier for you to grasp this. Because I'm giving you a 3-dimensional thing that's not hard to work with, but it might be very difficult to conceptualize. I have a circle centered at the origin, and I want to put a box inside the circle. Okay? It's not important that it's a square or anything else, but it's a box. If that point is x comma y, then I know that point is x comma negative y because of symmetry. That point is negative x comma negative y. That point is negative x comma y. Okay, does everybody agree with that? But that's not even the important part. The question is, how long is that? You went from here to here. How far is that?
2x.
It's 2x, because x is a positive coordinate. Oh, and then how far is it from here to here?
2y.
2y. Does that make sense? Okay, that was really easy. Now I want you to do this in 3D. Okay, then the third one would have to be 2z. Because I have this 3-dimensional thing that's going in all octants, centered at the origin. So if I'm positive in the x direction, then I want to go the exact same amount in the opposite direction. And x minus negative x is 2x. So that's why these are my dimensions. So this is the volume of the box. Okay? I am trying to maximize what? Am I maximizing this or am I maximizing this? I'm maximizing this. This is my constraint. Oh, I want you to build the box. But if I'd given you a different shape, you would have had a different constraint. But you'd still set up the box basically the same way. Okay? So, now that hopefully this part here makes sense. My 2-dimensional rendering hopefully helps you understand what the heck you're doing in 3D. Okay. The question is, I want to find the dimensions of the box, the rectangular prism, of maximum volume that can be inscribed into the circular ellipsoid. That's the correct verbiage here. Okay, I don't want any ambiguity there. Okay, so I have this egg. I want to put the largest such box. How do I know it's the largest box? Because it's the largest volume. So I want to maximize, let's call it V, volume. And what does V equal?
X squared plus y squared plus...
No, V.
Oh, that.
Yeah. 8 XYZ? Is the 8 important? Yeah, because without the 8, I would get a completely different answer. I'll give you a hint. Without the 8, I'll get something probably 1/8 as big. Yeah. Subject to x squared plus y squared plus 4z squared equals 48. I wanted this to have symmetry. If this shape did not have symmetry, or let's say that it wasn't circular, What if it was x squared plus 2y squared plus 4z squared? I can still ask the question, but it might not be a rectangular prism, or the vertices might not be touching. I might have something in the open air. If this room, let's just say this room were really long and narrow, and I wanted the largest sphere I could fit in, would that sphere touch all the walls if it were long and narrow? No, that would be impossible. Could it touch those two walls, the floor, the ceiling, and this wall? Yeah, but if I kept that wall going, it's not going to touch that wall if it stays a sphere, would it? I'd have to make it really skinny. So I do need certain things to be able to pull this off. So our first thing is to create a new function. How about we let g be x squared plus y squared plus 4z squared minus 48. Now, what is the gradient of v? Go slow, we can't afford errors here.
8x, 8y, 8z.
So what's the gradient here?
8yz. Oh wait, 8yz.
8yz,
8xz.
8xz,
8xy.
8xy. Good, good. What is the gradient of g?
2x, 2y, 8z.
And 8z. This is going to be interesting. So I've got 8yz, 8xz, 8xy equals lambda times 2x, 2y, 8z. And that gives us a set of equations, fairly simple to read. I have 8yz equals 2 lambda x. By the way, you can put the lambda in front. It really doesn't matter. Sometimes it's just easier to read this way. 8xz is 2 lambda y, and 8xy is 8 lambda z. Oh man. I have 3 equations there. I have 4 variables. What are we supposed to do? And now there's no constants I can multiply either side by to make this work. By the way, I am maximizing the volume of the box. Would it be safe to say that none of the x, y's, and z's could actually be 0? Because if x, y, or z were 0, then I have a box of 0 volume, which it's pretty obvious we can have a box with positive volume. So the variables being 0 is really not even an option, is it? I'm pointing that out because what if I wanted to multiply both sides of any of the equations by a variable? Huh. You know, these all look really similar. They all 3 almost look like 8xyz, don't they? Let's make them all look like 8xyz. To do that, what would I have to multiply this by? How about this one? Because. Oh, you said, oh, never mind. Yeah. Okay, is that legal? Yes, because we just said they cannot be 0. The only thing you cannot do is multiply by something that could potentially be 0. Well, why the heck would I do such a crazy thing? Because now I have xyz equals 8xyz equals, and then here. Right now the left sides are all identical. What do I have on the right? I have 2 lambda x squared, I have 2 lambda y squared, and I have 8 lambda z squared. Is that important? Yeah, it means that these 3 are equal. And if those 3 are equal, well, that's the nice thing. Then the lambda doesn't matter, does it? In fact, the 2 lambda doesn't matter, because they all have a coefficient of 2 lambda. Is that a good thing? Can I say right now that x squared equals y squared equals, sorry, not 8, but what? 4z squared. Can I say that?
Yes.
If this equals this, then multiply through by 1 over 2 lambda. Think of it that way. Lambda can't be 0. I don't know what any of them are, but I have this relationship. Where is this going? Here. So what do I want to do? Do I want everything in terms of x, in terms of y, or in terms of z? The answer is yes, it won't make any difference, it'll be the same amount of work. What do you prefer? Okay, let's go with x. I want everything in terms of x. So what do I have? I have x squared plus y squared, but y squared equals x squared, plus 4z squared, but 4z squared equals x squared. Isn't that nice? And it all equals 48. Are you happy with that?
Yeah.
Oh yeah, you should be dancing in the aisles right now. This is going to come out beautifully. Is the algebra difficult at this point? No, but what you didn't necessarily see was the trick that I did here I did not do before. What's the point? Think of optimization problems in Calc 1. Hopefully you did lots of them, and no two ever really felt like they looked the same, because there is no one size fits all. If I have a constraint, I have to work with it, but a lot of times you did a substitution, you did different things. Your end result was to find a maximum or minimum or both, but there was no one pattern or one type of problem that always was the same. Each problem I've done has been completely different. The only thing that I've done was the same, was to set up the Lagrange multiplier to get the equation. But then when I got my equations, it's okay, I need to solve. I have done something different each time. This time I multiplied by a variable. But as a result, we got this, which is, wow, beautiful. And it makes that answer really easy to solve. So this is what I now have. I have 3x squared equals 48. So x squared is 16. So x is x plus or minus 4?
Just.
X represented the coordinate in the first octant. So x has to be positive, doesn't it? X cannot be negative. Remember, my coordinates for x were x and negative x. Okay, so this is not a plus or minus, this is, no, I'm finding this coordinate right here. I'm finding this coordinate. And right now that coordinate is 4. So this would be the positive, because the way we set up the problem was we called x, y, z the coordinates in the first octant. So all three are positive values. We said they couldn't be 0. So therefore, based on that, what's y? Based on that, what's z? Let's see, 16 equals 4 times z squared, so z would have to be 2. I want to remind you, the way we set up the problem, again, we chose a point in the first octant, and then we did the mirrors in all the other, right? There were 8 vertices in all. So we said they were all plus or minus coordinates, but we have to start somewhere. So we chose x, y, and z to be positive coordinates in the first octant. So it appears that 4, 4, 2 is the ordered triple in the first octant. Do I now know the dimensions? Yes, what are my dimensions? 8 by 8 by 4. In this case, that means by. We know that. So what is the maximum volume I get? It'd be 8 times 8 times 4. Now, we know this is going to be the max. How do we prove it? That's easy. Pick anything that satisfies the constraint. How about we choose 0, 0, square root of 12. Would that work? Does that satisfy the constraint? And what is the volume of 0, 0, square root of 12? I believe it would be 0. We love problems like this because anything we check is probably going to give us a 0 for volume, and therefore our answer had to be the max. But we still have to prove it. Now, what if you said, no, I'm not going to choose 0. Let me pick random values of x and y. Maybe I pick x and y to both be 2, and then that would make z, what, root 10, and then I'll do that. Anything you chose is fair game as long as it satisfies the constraint, and we'd find we did not get as big a volume. So the maximum volume is 8 times 8 times 4, at 256 cubic whatevers. The dimensions of the box are 8 by 8 by 4. Okay, so there's a lot of ways I could answer the question. But it was really about the plan of attack over there. Okay? Any question? Crazy. But you like this? And by the way, we're using the gradient to solve problems. So this is one of the reasons the gradient is so important to understand. We used it for directional derivative, completely unrelated. Now we're using it to establish a relationship between the thing we're maximizing or minimizing and the constraint. That's just really clever, okay? Again, I wasn't there when they decided this. It was a couple years before I was born. A few centuries before I was born they did this. Okay? Maybe we can do one more. A common question that I get is, are there problems that we could do using the Hessian or doing the Lagrange multiplier? And the answer actually is yes. So how? We couldn't have done that one. In certain situations, if I have a function of 3 variables, like we just did, a function of 3 variables, but in my constraint, remember I did it a little while ago, z equals x squared plus y squared? If I go back to the original thing that I'm maximizing or minimizing and replace the z with the x squared and the y squared, don't I now have a function of 2 variables? And I'm asking you to maximize or minimize that? I could technically do the Hessian problem on that one. Now, what's going to be easier? This. This is going to be significantly less work. But you would still get the same answer if you did the other one. That's kind of cool that I could actually take a problem. But it has to be a situation where you actually have that going on for you. That's not an automatic thing. Okay? Let's find the extrema of f of xy equals 4x squared plus 8y squared, subject to x squared plus y squared equals 64. I have a 3-dimensional function. In fact, this is an elliptical paraboloid. We know that. It's not circular because those are the different coefficients. It's an elliptical paraboloid. It's 3-dimensional. But I have to, x and y have to come from that circle. We would think maybe this isn't that terrible. Or maybe it's hideous. So let's start the way we start every time. I know I'm maximizing or minimizing this, so now we create our 3-dimensional function. I tend to use g because most of the time the function you're maximizing or minimizing, they'll generically call it f. I just don't want to reuse letters. And again, the reason we create this is so we can have a gradient vector in 2 dimensions, because this gradient vector is in 2 dimensions. So that algebra is rather trivial. It's really about the y. Hold on, I'm going to find a pen with some life in it still. Okay. So everyone, let's find the gradient of f and the gradient of g. Hopefully at this point you're really fast at this part of the problem. So what's the gradient of f? 8x, 16y. What's the gradient of g? 2x, 2y. Okay, so now what do we got? Excuse me. Let me see. I'm trying to find something that gives us issues. And I did this intentionally. So what have we got right now? We've got 8x equals lambda times 2x. And we have 16y equals lambda times 2y. It appears that we have a problem, don't we?
Lambda is
Lambda
different
be 8
values.
and 4.
But lambda can't be 0. But can a variable be 0? Yeah, I chose this. This is one that appears like everything just went wrong. No, everything's right. But you're saying, wait, no, this can't be true unless lambda is 0. But if lambda is 0, what's the problem? Then the right side is 0, which would mean that x is 0. The right side is 0, which means y is 0. And 0, 0 is not going to work. Oh. Both x and y cannot be 0. Both of them can't be 0. Can one of them be 0? Yes. And that's how we're going to solve it. Okay. X equals 0 is a solution. If x equals 0 is a solution, then what does this say? If x equals 0, then what must lambda be? Excuse me. Then lambda equals 8 is perfectly correct. How about if y equals 0? Then what does lambda equal? 4. No problem with that either. Now, I want to show you that this still works, but I get potentially more than one answer. Oh, that we hadn't considered before. This problem appears to be evil at first because we're not sure what to do. Lambda cannot be 0. So if lambda is not 0, but x is, then lambda being 8 makes perfect sense. 0 equals 8 times 0. Or if y is 0, then lambda must be 4, because 8x would be 4 times 2x. So let's look at the two situations. In other words, I was showing you the consistency. If x is 0, we get something, y is 0. There's not a problem. I don't care about the value of lambda, but I just showed that this is a perfectly good solution, but I don't know what y is. Well, actually, I do. If x is 0, y is plus or minus 8. Yeah, there's no reason that x and y can't be negatives. Oh, so that would mean y is plus or minus 8, okay? That's two answers, by the way. That's 0, 8, that's 0, negative. Yeah, 0, 8, 0, negative 8 are both up there. If y is 0, then what's x? Also plus or minus 8. So right now, how many potential solutions do we have? We've got 0, 8, 0, negative 8, 8, 0, negative 8, 0. Oh my gosh. Like this, all right? Okay, go to your f function. What is f of 0, 8? It's 8 times 8 squared. That'd be 512. What's f? That's negative. Or that's also 512. Excuse me. 8, 0.
256.
That'd be 4 times 8 squared, which is 256. And there's my answer. You're not entirely convinced. That is the answer, but you're not entirely convinced. Is it okay to be not entirely convinced? Yeah. Tell me, Samuel, you're entirely convinced? No, you say no. So what can I still do? Pick a random point that satisfies the constraint. Okay. How about, let's use 4 comma square root of 48. That satisfies the constraint. What is f of 4 comma square root of 48? 4 times 4 squared would be 64. 8 times 48 would be 384, which is what? 448. Which is smaller than this one, but bigger than this one. I'll go out on a limb and say of the infinitely many points that satisfy that equation of the circle, every one of them is going to produce a value between these two. Every one of them. Which is why that's the max and that's the min. And this is what I had said earlier. When you get more than one, it's really easy because whatever's the biggest is going to be the max, the smallest is going to be the min. This one was kind of crazy, wasn't it? Because it appeared to be all wrong because it didn't look like the previous ones. But all you had to remember was lambda can't be 0. When you're looking at this, there's no contradiction with either of the variables being 0. That's why we're okay with saying, well, that would mean a variable had to be 0 if lambda is not 0. Yeah, but either variable could have been 0, and that's where this answer came from. So this one here, this was goofy. This didn't look like the others, but the consistency is still there. It still worked. Okay? Any question on this? Okay, this is considered, again, a major, major application. If I put this together with the Hessian that we did yesterday, the Hessian, remember, only works for functions of 2 variables. You wouldn't use it if you have 3 independent variables. But if I gave you a situation like this, is there any way that I could make this into a Hessian problem? Not really. Not really, but I could make it into a Calc 1 problem. Does anyone see how I could make this into a Calc 1 problem? Calc 1 problem meaning 1 independent variable. Just for fun. What if I said, why don't we let y squared equal 64 minus x squared? Then if I put that in here, wouldn't that just give me the equation of a parabola? Whoa. Now, what's the problem with the equation of a parabola? Probably not getting that many things, am I? But would I get the equation of a parabola if I replace y squared with 64 minus x squared? Yeah. Yeah, it would be an odd parabola, and I'd probably get, some of those would probably show up. I don't think they would all show up. But sometimes I can manipulate. I don't recommend doing that. If you have a Lagrange multiplier problem, I don't recommend trying to make it a Hessian problem, because that doesn't generally ever make it easier. If you have a problem where, yesterday, the only way I'm going to do it is using the Hessian, I don't recommend making it this problem. On the quiz that is due, I think it's quiz due tomorrow. Has anyone actually done that one yet? Did you try the bonus problem?
Yeah.
On the bonus problem, what did I say? Don't use Lagrange multipliers because we haven't learned Lagrange multipliers yet. The problem can be done using Lagrange multipliers. I didn't want you to. I wanted you to do it using the Hessian because that's the only vehicle we had. Now, I gave you a bonus problem from today's class that it's not the same problem, but actually looks very similar. But that one I want you to use Lagrange multipliers on because I want you to have 2 very specific techniques that you now can employ. And the reason is I gave you a situation. I didn't give you a graph. I didn't say here's a function and here's a 3-dimensional graph, find maxes and mins. I said I'm going to build an object and I want you to maximize volume or I want you to minimize cost or something. Oh, that means I have to create the function myself that I'm going to maximize or minimize. That's, by the way, in real life. I always say this sort of jokingly. In your Calc 1 class, if you're sitting here, I'm guessing you were probably pretty darn good at derivatives. Probably not too bad at integrals, but you were probably really good at derivatives because that's a lower level of reasoning, right? So you're going to get that first job as an engineer. You know what they're going to do? They're going to hand you a whole sheet of problems and say, find the derivatives. And then when you're done with the derivatives, you're going to hand it in, you're going to get your paycheck. Wouldn't it be great if it worked like that? They're just going to give you a bunch of math problems that you're used to solving. You solve them, turn them in, and you get paid. Pretty sure you're never going to see an equation. They're going to say, okay, here's the situation. We have this and this and this and this going on, and we need you to figure out what's going to minimize our costs or maximize our efficiency. And you go, wait, but where's the equation? What equation? No, that's up to you. You've got to come up with it. That's called mathematical modeling. In real life, no one's ever going to hand you the equation and say, solve it. They're going to give you the situation. You understand? That's what is the most hated problem at every level of math? Let's face it, what does everyone hate?
Words.
Word problems or applications. I call them applications. We hate word problems. Why do I have to do these? And I laugh, I said, if you didn't do it, what are you learning math for? You're learning everything abstractly with no application. No, the applications are the most important thing. Now you get to actually see where does the math get used. We don't like them. We want to be handed the equation and asked to solve it. But in real life, as you're given the situation, you got to come up with the equation and then solve it. Because that's how it really is in real life. So when I asked you, I gave you an egg and I said, build the box. I didn't give you equations. We came up with the equations, right? We built the problem ourselves. That's far more real life. So the bonus problems that you're turning in the next 2 days, That's really the whole point of all this. Now, I called them bonus problems because you have to set them up. But you're capable of doing it, and once you set them up, now you're using the math that you just practiced, and hopefully getting comfortable at it. Now, tomorrow we start integration, which is really, really huge. It's not that it's hard, it's just you have not done this, multiple integration. So we want to nail this and get this down, and that's the last material. The harder integration concepts are all after tomorrow's lecture, so they're all pushed to exam 3. So you're only getting an intro. So the integration that you're going to do on the test is a much lower level than you're going to do, let's say, for test 3. That's a good thing for you, by the way. You don't want the gnarly stuff right away. So if you can stay on top of things, I like that a lot of you guys are really, really fast. Some of you are almost too fast. You're turning in quizzes before we've had the lecture. I'm not sure that's a great idea, but at the same time, I would strongly recommend that you put yourself in a position that you've done a substantial amount of your review no later than Saturday. Then if you have questions, you can ask me. There's a tendency, especially in calculus, that we procrastinate. So I know that because you know what? I'm going to have a plethora of questions sent to me after 11 p.m. on Monday night. That's what always happens. For a Tuesday morning exam, yeah, I might get to the answer, but you might not see it in time. So that same question, I'd rather you ask me Saturday or Sunday so you have time to put it into play. Plus, having questions at the last minute does not make you comfortable for an exam. So getting to the practice test sooner than later. Again, this was the sacrifice you made when you chose to do a 6-week course. But most of you, I'm going to say most of you, it's fantastic. This class every summer tends to be really, really high end. Maybe not as high as my regular year, but certainly significantly higher than everyone else's Calc 3. I still hear horror stories from other people saying, I Calc 3 class and hardly anybody's passing, and thinking, really? Most of my Calc 3s, the average is an A. In this class, the average is an A. Right now, you know, more than half of you have A averages. In fact, I think still a fourth of you are over 100% averages. Those are the people you don't want to invite over. They're just no fun. You know, they get everything right and they make you feel bad. No, it's just because you guys are working and you're doing the right things. Don't let off the gas. But Monday's a holiday, so enjoy some time this weekend. So get your stuff done a little on the earlier side so you can. I don't want to hear that you spent 4th of July nose to the computer all day long. Do that on Sunday. Okay. Any questions before we finish on? Okay, let's go ahead and turn that off and do the roll.